Hello and welcome back to the alphabet of astronomy. Today is brought to you by the letter D, and D is for dark matter, of course. So what is dark matter? Well, we don't know, hence the name. But even though we don't know what it is, we still know a lot about it. Basically, dark matter is any sort of matter that has mass, i.e. it interacts with gravity, but doesn't interact with electromagnetic radiation, i.e. light. So that means it doesn't reflect it, it doesn't absorb it, it doesn't emit it, it just totally ignores light. But gravity, it does interact with. Okay, so if we can't see it in any way, how do we even know that dark matter is there? Well, there's actually a few different methods that we use to infer the existence of dark matter. So one of the simplest methods is to look at orbits. So orbits depend on the mass of the object. You can look at Newton's law for this. And so if we can look at the orbital velocity of something, we can tell how much mass it's orbiting. And if you do that and then compare it to how much luminous matter, i.e. matter that's not dark matter, we see that it doesn't match up. That is, the gravitational amount of matter has to be more than the luminous amount of matter in order to explain the orbital velocities that we see. This was very famously done by Vera Rubin and her collaborators in the 1970s when they observed the rotation curves of galaxies. Now, most of the luminous matter in the galaxies is in the center, and so as you move away from the center, you expect the rotational velocities to start to fall off because you're getting farther away from the matter, and there's not any more matter, really, that it's orbiting. However, what they found is that the rotation curves were actually flat. That is, as they moved away from the center, the rotational velocities still maintained high even though they were farther away from the luminous matter, and there didn't seem to be enough luminous matter out there to explain it. So there must be some kind of matter that isn't being accounted for just looking at the luminous matter. You can also see similar behavior when we talk about the motions of galaxies within clusters. Basically, these clusters are gravitationally bound, but based on the speeds that we observe these galaxies moving, if there was no dark matter, they would just fly apart. But they don't, so there has to be some sort of extra matter there that's maintaining that gravitational bound, even though we can't see it. Okay, but I said that orbital velocity is based off Newton's law, and we know that Newtonian gravity isn't the whole story. So does general relativity do any better? It does not. And in fact, using general relativity, we can use lensing to determine that there actually is dark matter as well. So lensing is basically using the curvature of space-time due to general relativity as a lens, and that amount of bending is dependent on the mass. And so based on the amount of bending we see, we know that there's more mass than is contained in the luminous matter that we see. Okay, so maybe general relativity isn't the whole story. And there have been a lot of theoreticians that have worked on this and tried to come up with alternative explanations to these observations that we think are due to dark matter that don't invoke any additional matter that we don't see. For example, MOND, which is modified Newtonian dynamics. However, none of these theories so far have been able to explain all of the observations, and there has not been a successful cosmological model that uses these theories. Okay, so we're pretty convinced that dark matter exists and that it is actually matter. And one thing that's crazy about it is that there is a lot of it. There's actually way more dark matter than there is luminous matter. We think that dark matter accounts for about 85% of the mass in the universe. And if you look at the whole mass energy density of the universe, it's about a quarter. There's a lot of dark energy in there, which we're not going to get into in this video. Okay, so hopefully you're convinced that there is some sort of matter out there that we cannot see. So maybe, you might think, this is just regular matter that happens to be very dark. Maybe something like black holes or rogue planets or things like this. So this was actually once a very popular and leading theory, particularly these objects called machos, which are massive compact halo objects. However, observations have basically ruled out the entire parameter space for machos, and so we don't think that they can explain dark matter. So I mentioned cosmological models before, and I said that the kind of modified gravitational theories can't really be incorporated into a cosmological model right now. So basically, the leading cosmological model is something called lambda CDM. And I'm not really going to get into the details except to say that CDM stands for cold dark matter. So our leading cosmological theory includes dark matter, and it includes cold dark matter. So what does that mean? Well, we're not really talking about temperature exactly, we're talking about the dynamical heat of these objects. So that basically means that they're moving slowly, i.e. not at relativistic speeds, which would be hot dark matter. So a lot of very intelligent theorists are trying to work in various types of dark matter that could work in both the observations that we see and in our theoretical lambda CDM model. There are a lot of theories out there, and I'm not going to get into the details, but I'll tell you some of the top contenders. One is WIMPs, gotta love the acronyms, which are weakly interacting massive particles. There are also axions, sterile neutrinos, SIMPs, which no is not just kids these days slang, it's actually strongly interacting massive particles, and a really crazy one called PIDMs, which are Planckian interacting dark matter. So these are all different particles that are being proposed. So they basically would fit into what we call the standard model, which is all of the particles that we know of in physics. However, a lot of particles are investigated and detected using colliders. So for example, you may have heard of the Large Hadron Collider at CERN. And none of these dark matter candidates have so far been detected, even though we were kind of expecting some of them to show up in these colliders. And it's not just colliders. We've used other detectors to try and detect some of these various particles. Similar to how I talked in a previous video about how neutrinos are very difficult to detect, but we've managed to do it. So scientists have done similar sort of experiments for these dark matter candidates, but so far there has been not a single detection, not one, zip, zilch, nada, despite quite a lot of effort. But what these direct detection attempts have done is really narrowed the parameter space in which we think this particle might exist, because if it existed in a certain way, then we would have detected it. So the fact that we haven't detected it kind of narrows our search. And as we continue to get better technology and more money and better theories, we can kind of really zero in, hopefully, on what these dark matter particles actually are. And so this is an area of extremely active research and interest in the entire astronomical community. There's so much information out there about dark matter. This was really just a very tip of the iceberg, kind of like luminous matter compared to all the matter in the universe. So I hope that you learned a little bit about dark matter, and I hope you will join us for the letter E, and I'll see you again next time. Bye!